So these are the outline of this session. So we will quickly review what a cryptographic hash function is, and then we will dive into two scenarios where hashing is used in for security. One is message authentication code, and the other one is digital signatures. So last time we've seen hashing is nothing but kind of extracting fingerprints from a document. And the basic idea is we use a hash function. It takes a variable size message and produce a fixed size hash value. This fixed size hash value is also known as the message digest. We usually, for using hash functions in cryptographic scenarios, we want to use a hash function that is efficient in computing. It can be done very fast. And also we want a function that produces pseudo-random values, which means a small change in the text results in a big change of the hash. Then we explained two major properties that a hash function should satisfy. The first one is the one-way property. Given a hash, it should be infeasible to produce the message that was used to create this hash. The other property is the collision-free property. We shouldn't have any two messages. It should be infeasible to find two messages that has the same hash. So, and then we started looking into, let me show you. I think I showed you some small examples. Here is the one, is hashing. So just super quickly, just to remind you, when I run this one, you can see although these two messages have only one dot difference, the hash is completely different. And in here I'm using SHA-256 as the hashing algorithm. If you recall, one of the properties of a good cryptographic hash function, it should not have collisions. We should not be able to find any two messages that produce the same hash. So I managed to find one example. If you recall MD5. So MD5 is vulnerable. Is no longer a good cryptographic function because people manage to find messages that has the same hash, which means MD5 has message collisions, and this is not good for cryptographic usage. So just to show you, this is a super small example. If you can see here, these messages are very similar, except there are some differences. You can see here I have 8, and in the other message I have 0. And there are some other small differences. So really, this should have produced different hash. But surprisingly, if I use MD5 as a hashing algorithm, these two slightly different messages, they produce exactly the same hash. This is what I mean by collision. This is an example of collision. Now, if I take this example, and instead of using, let's say MD5, which is vulnerable to collisions, if I use, let's say even SHA-1, if I rerun this, you see using SHA-1, the hash is completely different because the two messages are slightly different. But using MD5, it produced the same hash. So, and that's why MD5 is no longer considered cryptographically secure because it can produce collisions. So I hope this idea of collision-free, it's clearer now. So this is just kind of an analogy of what really hashing is. You take a big message, you take it through some kind of compression function, and then you produce a fixed length hash that is really representing a fingerprint of the original message. And it is one way. From this hash, you cannot produce the original message. Now, there are many hash functions, as I explained last time. Some of them are no longer recommended, such as MD4. SHA-1, also people find some collisions for SHA-1. SHA-2 is widely used, especially this one, SHA-256 is widely used, and there are minor issues with this. There are minor issues with this algorithm, but still, NIST has already a much better algorithm for hashing with known collisions and no known attacks, which is SHA-5. It's only recently has been approved as a new standard. So, but in reality, people are still using SHA-1. It is still acceptable. SHA-256 is also widely used, and gradually applications will be moving to SHA-3. More and more libraries and languages are supporting this new standard. Now, we will not dive into these algorithms, but just I wanted to bring the idea of hashing a bit closer to your mind. How does it really works? This is very high level, of course, and very generic. These algorithms use much more sophisticated techniques, but we can summarize them using this figure here. So what you do is you have, let's say, a large message M, and you want to hash it. So the first thing is you break it down into blocks. Now the size of the block depends on the hash algorithm. Each hash algorithm has different block size, similar to encryption. Like for example, for DAS, for encryption, we use the block size 64 bits. For AES, we use a block size of 128 bits. In here, it depends which algorithm we're talking about. So you chop it into blocks, and then for each block, you pass it through a function, a compression function. That block will be compressed, and you produce, from it, you produce an output that has the size of the hash value. Remember, each algorithm, at the end of the day, produces a hash value of fixed size. Let's say for SHA-1, I think 160 bits. For SHA-2, there are many multiple sizes. The most common is 256. So at the end, from each block, you pass it through this compression function. It squeezes it into the size of the hash value. Then the output is fed to the next compression function, or it's fed to the compression function. The compression function takes two inputs. It takes the block and it takes the previous, let's say, hash value, the hash value of the previous block. So you might be wondering, what about the first block? The first block, we feed it an IV. So for each block, you feed it to the function, the compression function, and you also feed the hash value of the previous block. And you keep doing this. And at the end of the day, the hashing of the last block will be your final hash. And because of this feedback, that is, you are feeding back the hash from the previous block, you are basically taking the fingerprint of the whole message will be reflected in the compression of the last block. That's basically roughly how really hashing works. Of course, inside the F, that's how each algorithm do it differently, but they all most of them will use the normal tricks of cryptography, which are substitution, permutation, repeating things multiple times inside the F function. So that's roughly how it works, how the hashing works. If you are interested into the details of how each of these algorithms work, I think Wikipedia has very nice explanation, concise explanation of each of these algorithms. But it's not really needed. At least you basically get familiar with the overall structure of a hash algorithm. Then, once we understood what really hashing is, what are the properties of a good cryptographic hash function, we started looking into where do we use this hashing, what are the application areas. And we identified, in terms of security, these three major areas: message authentication, digital signature, and password storage. These are security-related application areas of hashing. Then there are many other areas, such as detecting errors in file transfer and also generating a random number. So let's start with the simpler ones. I already explained last time, if we recall, if we go, now I have a full example I can quickly show you. Like if I go here, search for WebStorm. If I go and try to download WebStorm, so it will give me the download link and also a hash value associated with the file. This is my hash value. So what I can do, I can take this hash value. I wrote a very small Python program. Here is the hash in a large file. So what I did, I copied the hash that was provided by JetBrains in their website. And then after I downloaded the file, because it is a large file, I opened it. I opened the file. And then I started reading block by block. Each block I read 65,536 bits. You can put any size you want, depending on the capabilities of your device. Then I keep looping through. So I created an instance of SHA-256, and I keep updating keep hashing the blocks that I have read, and keep updating the hash. And at the end of the day, keep reading and keep hashing, updating the hash, and then finally I'll say, here is the hash that I produced myself after downloading the file, and here is the hash coming from the source, and I compare them. If they are equal, then the file transfer was successful, otherwise the file transfer failed. So if I run this, so you can see here is the hash. Here is the hash that I produced using the downloaded file, and here is the hash coming from the source, and I compared both, and they are equal, which gives me assurance that the file I downloaded is exactly the same as the one provided by, in this case, JetBrains. I can also do it in a much simpler way, also using OpenSSL. So if I go here and say PowerShell, and then I'll go to, I downloaded it here, so let me just go to that location. And then all I do, open SSL, and then SHA-256, and then I'll go for WebStorm, the name of the file. And you can see here it's produced for me the hash value. If I compare it, so you see here it ends with 23E3, yes? So if I go to their website, it's end with 23E3. Okay, so there are many utilities out there, but OpenSSL is the most widely used. Plus, it is implemented in all platforms. You can use this in Mac, Windows, and so on. So you can either check it using an online, like a command line utility, or you can write a little program to do it. In most languages, you are familiar with Java or or C# or Python or JavaScript, you have this built-in hashing functions already implemented. You just go ahead and use them. So I hope this is clear, like in terms of detecting file transfer errors. The other area where we use hashing is pseudo-random number generation. This is very simple. What you do, you first create an IV, which is a random value. You hash it, it produces for you another random value. You keep hashing the results. And each time you hash, you have a different value, really random. So that's another area where you can use hashing. Now let's start looking at using hashing for security purposes. Let's start with this simple scenario or a simple use case where we use hashing to store passwords. And this is what I explained last time. So the way you do that, you take your password, you add to it a salt value, which is a random value, and then you hash this concatenation of the password plus the salt. And the result is what you store in your database. This is just to demonstrate that if I use a different salt value, I will get different hash. And concatenating a salt value with a password, then doing the hashing, will protect you from dictionary attacks. And I explained this already last time. So now let's focus. Yes, please.
In that case, how would you get that salt value again if you want to compare the password again to this value?
Very good, yes. So of course, like this salt value you will store it. It's a secret. In this scenario, it becomes like a kind of a secret. You definitely don't put it in the same file or table as the hashed password. Maybe you put it somewhere as a secret. You need the salt value, otherwise you cannot recover. You can never recover the original password. But the way you do it is when somebody logs in, they will provide their username and their password. What you do, you take their password, you add the salt, and you hash it. Then you go to your database and you do query. You say select from users where username equal the username the user provided, and hash password equal the hash password that the user supplied. But from this hash, we can never recover the original passwords. Yes, so to summarize, I think this is a bit confusing. We never store, of course, the salt value in the same location. Otherwise, we are defeating the purpose. Like if the attacker comes in and get this file with the salt values, they can do dictionary attacks. So salt values, we store them separate. Or it's secret. It has to be kept secret, the salt value. Because we use it every time we want to do validation of logins. We have to take the password supplied by the user, add the salt, and then hash it. Okay, so what is now left? Two major applications where we use hashing. The first application, we use hashing in combination with symmetric cryptography. Remember symmetric cryptography, we have a shared key. So what we do is when we produce a hash, before we produce a hash, we take the message we want to hash and we add the key. Then we hash. Okay? And when we send the message to the other side, they will do the same. They will basically take the message, add the hash, and then encrypt. Take the message, add the key, then do the hash. I will explain what this means. So we are basically, let me say it one more time, I think we are combining hashing plus symmetric key to achieve these two properties, which is the integrity and the source authentication. I want to make sure the message that I am receiving did not change in transit, and I want to have some assurances that it's coming from somebody who has the shared key. And the people who has the shared key, I kind of know them. I know them. I know they have the shared key, same key as me. So this gives us these two assurances but the sender can still deny. It does. So the message authentication, it does not give us non-repudiation. So for us to achieve non-repudiation, we have to combine hashing plus asymmetric cryptography, which means we take the message, we hash it, then we encrypt the hash using public key. Then the private key. Then the recipient can decrypt it using the public key. So using digital signatures, I can achieve three properties: integrity, source authentication, and non-repudiation. I will explain these in more detail. For now, what I want you to kind of get as a first step is that when we combine hashing plus symmetric cryptography, what do we get? Message authentication. If we combine hashing plus asymmetric cryptography, what we can produce? Digital signature. In the first case, we can get these two services, integrity and source authentication. In the second case, in digital signatures, I can achieve the three properties: integrity, source authentication, and non-repudiation. So this is in high level. Now let's go into the details of each one. Okay. So here is the basic idea of what this message authentication code, it's also called MAC, message authentication code. The basic idea is I take the message plus the hash and hash both of them. Then I produce a MAC. So the hash value that I produce, it's called, I no longer call it a message digest, or I call it a hash value. It has now a special name, which is, it is a MAC. It is a message authentication code. So, and then what I do, I send the message along with the MAC. Do I send the shared key? No, the shared key is a top secret. I never send it. Now the recipient, here is our eavesdropper. Okay? The recipients, they will do exactly the same. They will take the message plus a key, hash both, and compare the output of the MAC received with the hash produced. If they match, what assurance this gives them? Two things. The message did not change along the way, because even if the attacker or the man in the middle receives the message and they change it, let's say, if they change it, they don't have the key to be able to produce the MAC. So if they change it, the recipient will know that the message has changed. Because for you to produce this MAC correctly, you must have the key. Because they don't have the key, they will never be able to produce the correct MAC. So that's why when we do this check, we will find out exactly if the message was changed or still intact. The other thing we know, let's say this is Alice and Bob receives this message. It gives them assurance that this message came from Alice, because Alice, she's the one that has the shared key. She has the same shared key. But Bob, if there is some problem, Bob cannot take her to court. If he take her to court for some reason, she denies sending a particular message, he has no evidence, because he also has the shared key, and the court will tell him, you might have produced this message yourself, and you put in the blame on her. So for us to achieve non-repudiation, we have to use asymmetric cryptography, which is basically digital signatures. But if we don't have this issue, if this is good enough for us, non-repudiation is not very important, then MAC is very good. We can just go with this. But be aware that we are only achieving these two properties or two security services, which is integrity and authenticity. So these are the properties of a MAC. So a MAC, at the end of the day, it is it uses a cryptographic function, and it produces a fixed length authentication tag that we call a MAC. It's just the terminology here. We're still using hashing. The only difference is we are combining the shared key with the message before we do the hash. And the value produced, we no longer call it a hash value, we call it a MAC. And it relies on a symmetric key. So for you to talk about MAC, you must have a shared key on both sides. And these are, as I explained, it ensures integrity and ensures authentication, source authentication, but not non-repudiation. It does not provide non-repudiation. So one naive way of doing it, there are many ways of doing it. One naive way of doing it is you take the key, you concatenate it with the message, and then you do the hash of key plus. Either you put the key in the as a prefix in front of the message, or you append it to the end of the message. One of the two. So this naive way of doing it is vulnerable to attacks. For us to understand those attacks, we have to go much deeper. We have to dig into the hashing algorithms. But definitely people have proved that this way of doing it can be attacked. Now, for better security, for making it 100% secure, people use a more sophisticated version, not just taking the key, concatenating it, and hashing. You need much more. And this much more is basically called HMAC. So we don't just use MAC, we use HMAC. And HMAC is basically an algorithm that was invented in 1996. And it's also called a keyed hash message authentication code. So it is used to ensure data integrity and authentication. And you can use the HMAC with any of the hashing algorithms. That's why when you refer to this HMAC, you will say HMAC SHA-256, HMAC SHA-3, HMAC H1. It means we are using symmetric key with one of these hashing algorithms. Now let's look at how the hashing really works. This is the algorithm, how it works. So we start with the key. Remember, this is a shared key used on both sides. The first thing, we produce two keys from this key. So we initially have one key. The first thing, we need to produce two keys. How do we produce these two keys? We take the key and we XOR it with a constant value. In case of, by the way, this is called an iPad, which is the inner padding. And this one is called the out pad. Big names, but all they mean, the outer pad is a fixed, it's a block that has this constant, 5C, 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 5C. Now the size of the block depends on which, hashing function you are using. Each hashing function has different block size. But it doesn't matter. At the end of the day, the basic concept, you take the key, you XOR it with a fixed length, 5C, 5C. You repeat it as many times to fit one block. You XOR these two, and you produce key 1. And key 2, you do the same. You take the key, you XOR it with another constant value. This time is 36, 36, 36. So you have series of 36, you XOR both. So at the end of this first step, what do you get at your hand? Two keys, K1 and K2. We also call them IK pad and OK pad. It doesn't matter, two keys. What do you do with these two keys? First is you take the first key, you concatenate it with the message, and you hash both. You hash the first key plus the message. You concatenate both and you hash. It gives you the first hash value. Then what you do, you take the second key, you concatenate it with the hash value, and you do another second pass. or a second hashing. Then you produce the final hash. So it's basically a three-step algorithm. Take the key, produce from it two keys using a XORing with a constant value. Then take the first key, concatenate it with the message, hash it. Last step, take the second key, concatenate it with the hash produced, hash it again, and produce the final hash. That's basically the HMAC algorithm. Is clear? This is provably secure, cannot be broken. Okay. So let me show you an example here. Of course, in practice, it's much easier. So all you do here, you say, this is the message I want to hash. Here's my key. This is a shared secret key. And then I say, I'm using Python here. There is a library called HMAC. You will find similar things in Java, C#, so on. So what I'm saying here, create an instance of this HMAC, give it the key, give it the message, tell it which algorithm you want, which hashing algorithm you want to use. You can use any of these algorithms, SHA-1 or SHA-256 or SHA-3, any of the algorithms. So let's just use SHA-256. So in this case, we will call this algorithm, really, we can call it HMAC SHA-56, SHA-256, or it could be HMAC SHA-1, or HMAC MD5. And that's it. You go ahead and then you say, go ahead and generate for me the MAC value, the HMAC. Go ahead and generate for me the hash value. So if I run this, this is my HMAC. Now when I send the message, I also send this MAC value with the message. And the recipients will be doing the same. They will do the same to make sure, to ensure integrity and to ensure source authentication. But of course, for them to be able to do the same, what they need to know? They need to know the key. The key, I'm not sending them the key, they must know the key. We share the key already. Either using Diffie-Hellman or we're using RSA, we already established the key. So I hope this is clear. So just to summarize, this is the naive way of doing it, just concatenating the key with the message. A more realistic way of doing it is using HMAC. It uses this two-step hashing or two passes of hashing. That's one way of producing the MAC. One way of producing the MAC, which is the message authentication code, in a secure way. One way is to use HMAC algorithm. The other way of creating an HMAC or a MAC, which is a message authentication code, is to use a block cipher in a CBC mode. I hope you remember the CBC mode. So block cipher, you can use any block cipher, like DAS or AES. And what you do is you take your message, let's say we use AES. We take the message, as you know, we chop it into blocks. What is the block size of AES? 128 bits. Okay, so the first thing, let's say we want to encrypt M2 using AES in CBC mode. So to encrypt the second block, we first XOR it with the encrypted value of the first block. Then we go ahead and do the encryption. So basically, the encryption of each block is fed back to the next block. Now, the first block, if you remember in the CBC mode, we used to provide an IV. And we XOR it with the first message to produce the encryption. In case we are using CBC or block cipher in CBC mode to produce the MAC, we don't really need an IV. The IV could be just zeros, an IV of all zeros. Now, we keep doing this. We keep Basically, we keep encrypting the message in CBC mode, and our MAC is the encryption of the last block. The encryption of the last block will be the MAC. Did you get the idea? So basically, we are using a block cipher to produce a MAC value. So then, this MAC value, we will be sending it to the recipient for them to ensure integrity and source authentication. Basically, I encrypted the message. The only difference here, using, let's say, AES and CBC mode, the only difference is the IV. The IV is initialized with zeros, not with a random number. Now, the encryption of the last block is my MAC that I will be sending along with my message. Yes? So basically, the difference is when I'm using AES to encrypt in CBC mode. Of course, the encryption is the output of each block. I put it together to produce the encryption. But if I'm using it to produce a MAC, I don't care about the encryption of all blocks, only the last one. The encryption of the last one is my MAC. I don't care about the encryption of the previous blocks. Now, if I'm using AES, what will be the size of the MAC if I'm using AES? It will be 128 bits because remember the AES, the block size of AES is 128. So at the end of the day, and you can see here, the last block will have the fingerprint of all the previous blocks. Why is that? Because we are feeding back. You can see here. That's why that's why the best way to think about hashing is fingerprint, because really it's super clear here, very clear that the encryption of the last block is influenced by the cipher produced by previous blocks. So really, the encryption of the last block is a representative hash or a representative fingerprint of the whole message. Yes? Is clear? So to summarize, how can I produce a MAC? Can we now summarize this? What are the two ways I can produce a MAC? So either I will use a hash function combined with a symmetric key, and in the most widely used algorithm in this case is HMAC. It will use a concatenation of the message plus the key to produce the hash. The other way to compute a MAC is to use any block cipher in CBC mode. We call this CBC MAC. And in this case, when I'm using block cipher, my MAC, what will be the MAC that I will be producing? How do I produce the MAC? I go through and do the encryption with the CBC mode, and the output of encrypting the last block is basically the MAC that I have. Okay, so let me summarize this. So MAC, or message authentication code, provide two security services. It provides message integrity and message authentication. And it relies on symmetric key. You must have a symmetric key for you to do this, to produce a MAC. Now, the difference between MAC, message authentication code, and digital signature, what's the difference between the two?
It provides
Yes, very good. Digital signature provide no repudiation. What else? Yes, for MAC it uses symmetric keys, which is the same key on both sides, while digital signature will use the private key to encrypt and the public key to decrypt. Okay, so as I explained here, MAC does not provide non-repudiation. In practice, it could be either we can produce a MAC either based on block cipher. We run this block cipher on CBC mode, and the encryption of the last block is our MAC, or we can use a hash function, combining symmetric key with a hash function. And typically, the most secure way of doing it is to use the HMAC algorithm. And I explained this algorithm previously. And the HMAC is the most popular way of producing MAC. And it is used in many protocols such as TLS. The TLS, transport layer security, this is used when using HTTPS. In our next session, I will be introducing this just to show you an end-to-end application of cryptography using a real protocol, which is HTTP. It combines all what we have seen. It combines symmetric cryptography, asymmetric hashing, MAC. It combines all this in an end-to-end solution for securing message exchange, web-based message exchange. So that's the MAC. The last thing I want to introduce here is the digital signature. So digital signature, again, very, very easy. We take our message, we take it through hash algorithm, maybe SHA-256 or whatever algorithm we wish, and then we produce the hash. We take the hash and we encrypt it using the private key. Then we take our message and we append the signature, similar to the real world. Real world, when you have some important document, put the document, and at the end, you sign it and you send it off. Now the recipient, here is our eavesdropper is always there watching. So they might want to try to change the message, because here we are trying to protect authenticity, integrity, and non-repudiation. So they might intercept the message, they try to change it. Even if they change it, they cannot produce the signature. Why they cannot produce the signature? They don't have the private key. So the recipients, when they receive the message, they will take the message. The message could be encrypted. It doesn't. They will decrypt it. They will get the original message. Then they will hash it. Once they hash, they produce this hash, okay? In parallel, they take the signature. Signature was encrypted using the private key. We decrypt it using the public key, and we get the original hash. And then we compare the hash that we produced based on the file, based on the document we received, and the hash that is produced by decrypting the signature. If they match, then we are 100%. These three properties are assured. If there is no match, this message will not be accepted to us. This message will be rejected. Yeah. So it produces authenticity. We are 100% sure the message came from the sender. It ensures integrity. We are 100% sure the message did not change in transit. And also the sender cannot deny. Even if there is a problem, they send us an order for a pink card, and they change their mind. We go to court, they cannot deny it. They send us the order of the pink card, we produce the pink card. If they change their mind, they cannot just lie to us. We have evidence. This is the non-repudiation. Okay, so this is what I just explained. That's it. I think that's very clear. These are these are the services that are ensured by digital signature. Okay, let me just summarize this very quickly. So, to summarize, in real life we have this hashing. It is a separate concept. Has many applications. We take that hashing concept, we brought it along and we united it, combined it with cryptography, symmetric and asymmetric, and we had very interesting applications when we combined these two technologies. So if we combine symmetric cryptography with hashing, what do we get? Message authentication code. If we combine hashing with, and this message authentication code ensures for us integrity and source authentication. Now, if we combine hashing with asymmetric cryptography, we get digital signatures. It provides for us the three services, which are the integrity, source authentication, and non-repudiation. That's basically the idea. The last thing here, the last thing that is really left for us to complete the picture is digital certificates, which is different than digital signature. And I will explain this one next time. And that will be the last. And then I'll put all together in HTTPS as a protocol that combines all the cryptographic suites and tools in one solution.